Hello and welcome to Chapter 18 on Quasars and Other Active Galaxies. The story of Quasars started when we found black-body radiation that peaked in the radial range rather than what we would expect, which is generally the visible range for stars that are like our Sun, or at least closer to the visual range. And what occurred was that they didn't know where this black-body radiation was coming from and where the spectra were coming from, because it didn't match the spectra for any known elements at the time. However, in 1963, Martin Schmidt at the California Institute of Technology discovered that it was actually just the spectrum of hydrogen with a very, very high redshift, meaning that the stars that it was coming from were going very, very fast. This redshift corresponds to a speed of almost 16% the speed of light, corresponding to a difference or a distance of roughly 2 billion light years away by the Hubble constant that we were talking about, or the relationship distance and speed that we were talking about in the last chapter. Because of their star-like appearance and strong radio emissions, 3C40 273 were dubbed quasi-stellar radio sources, which was soon shortened to quasars. Related objects called quasi-stellar also look like stars, but have strong energy outputs of different parts of the electromagnetic spectrum, with the most strong being in infrared. Galaxies are big and bright. A typical large galaxy, like our own Milky Way, contains hundreds of billions of stars and shines with luminosity of 10 billion suns. The largest and most luminous galaxies, the giant ellipticals, are only 10 times brighter. But beyond 8 billion light years from your Earth, even the brightest galaxies are too faint to be detected. Most ordinary galaxies are too dim to be detected at half that distance. If quasars can easily be seen by 13 billion light years away, they must be far more luminous than normal galaxies. Indeed, a typical quasar is 100 times brighter than our Milky Way. In the mid-1960s, several astronomers discovered that quasars fluctuate in brightness. Going back from old images, they found that some newly identified quasars had actually been photographed in the past, but they had not been seen as anything special because they looked like stars. One photograph, for example, dates back to 1887. By carefully examining these old images as well as recent ones, astronomers could see that quasars occasionally flare up. Prominent outbursts from quasar 3C279 reached Earth around 1937 and 1943. During these events, the luminosity of 3C279 increased a factor of about 25. At peak periods, it was emitting at least 10,000 times as much energy as the entire Milky Way. If the same fluctuation traveled more slowly, then the object would have to be smaller than half a light minute across for it to return to its original state after 1 minute. Therefore, the object could not be more than half a light minute across, which is how we find the minimum depth or the minimum breadth of an object, by seeing how, when something crosses in front of it, how fast or how long it stays dim, with the minimum amount being 1 light, half a light minute across for returning to the original state after 1 minute. In this way, astronomers can calculate the maximum size of an object can have from the timescale of its fluctuations. Many quasars vary in brightness over only a few months, weeks, or days. In fact, X-ray observations reveal large variations in as little as 3 hours. This rapid flickering means that the source of the quasar energy must be quite small by galactic standards. The energy-emitting region of a typical quasar, the powerhouse that blazes with the luminosity of 100 galaxies, is less than 1 light day in diameter. Quasars are but one kind of very powerful energy source in space. The others include safe-air galaxies, radio galaxies, double radio sources, and BL-Leclerc galaxies. Located at the center of these galaxies are powerhouses collectively called active galactic nuclei, or AGN. The galaxies that contain AGN are called active galaxies. Safe-fair galaxies reveal exceptionally bright star-like nuclei and strong emission lines in their spectra. For example, the rich spectrum of NGC 4151 has many prominent emission lines. Some of these lines are produced by iron atoms with a dozen or more electrons stripped away, indicating that NGC 4151 contains some extremely hot gas. Some elliptical galaxies, called radial galaxies because of their strong radial emissions, are like lower energy quasars. Although their energy source is very small, like that of a quasar, the resulting radial emissions of these active galaxies are spread out over very large areas, often hundreds of thousands of light years across. Some radial galaxies are accompanied by unusual optical features, namely, the galaxies look as though they are exploding, which they are not. Such galaxies are called peculiar galaxies, denoted as PEC. Peculiar is not a classification of a galaxy shape like spiral, barred spiral, elliptical. Any of the Hubble classes of galaxies can be peculiar. Detailed observation of Centaurus Centaurus A revealed that both its radial and X-ray jets originated in the galactic nucleus. Particles and energy stream out of the galactic nucleus towards the radial lobes at nearly the speed of light. Such galaxies with two radial lobes are now called double radial sources. All double radial sources appear to have a central engine that ejects electrons, protons, and magnetic fields outward along two oppositely directed jets. After traveling many thousands or even millions of light years, this material slows down, allowing the charged emissions and magnetic fields to produce the radial radiation that we detect. This type of radial emission, called synchrotron radiation, occurs whenever energetic electrons, protons, or ions move in the spiral path within the magnetic field. The ideal that a double radial source emits jets of particles and supported by the existence of the head-tail sources, so named because each source appears to have a region of concentrated radial emissions, the head, with two tails or jets of gas that stream from it in opposite directions. Although radial galaxies emit less energy from their nuclei than do quasars, there are also objects of the same size from our vantage point emit even more energy than quasars. They are called BL Lacertae objects. The name comes from their prototype BL Lacertae, also called BL Lac, in the constellation Lacerta, the lizard. BL Lac was discovered in 1929 when it was mistaken for a variable star, largely because its brightness varies by a factor of 15 in only a few months. BL Lac's most intriguing feature is an unusually weak set of spectral lines. In other words, its spectrum is not easily identified as those of stars or interstellar clouds. Nonetheless, the spectra enable astronomers to determine the redshifts of these objects. BL Lac galaxies are believed to be elliptical galaxies with bright quasars at their center. Much as safe-fair galaxies are spiral galaxies with quasar-like centers, BL Lac objects change intensities. They are variable. Those that have periods of a day or less are also called blazars. In 2017, 5 blazars located between 12 and 12.5 billion light years away were discovered. It is intriguing that this massive object came into existence only a billion years after the universe formed. The gravitational energy associated with supermassive black holes at the center of galaxies creates huge jets of gas comprised of protons and electrons. To see how this works, consider a black hole at the center of the galaxy filled with gas and dust. Because the center of galaxies are congested places, a black hole located there will capture a massive accretion disk of this debris. If the black hole is not rotating, it's a Schwarzschild black hole, or if it is slowly rotating Kerr black hole, then most of the mass approaching it from this accretion disk will spiral down into it. This does not last for long because as the debris spirals in, the black hole gains angular momentum from the spiraling debris and therefore begins rotating faster and faster. By the time the black hole has doubled its original mass, its event horizon is whipping around at nearly the speed of light. The gas and dust spiraling towards a rapidly rotating Kerr black hole has much more difficulty entering the black hole because the motion of the black hole literally drags the space and debris around it and surrounding it around and around, thereby slowing the infall. The formation of jets occurs in this debris. According to Kepler's third law, the material in the inner regions of such a disk orbits most rapidly. The inner matter, therefore, constantly interacts with more and more with the more slowly moving gases in the outer regions, and the friction between them heats all of the gas. As energized gases spiral towards the black hole, they are compressed and heating to millions of degrees. In the vicinity of a rapidly rotating carrier black hole, this temperature creates great pressure, causing some of the hot gas to expand and eventually squirt out where the resistance to its expansion is lowest, namely perpendicular to the accretion disk. Like you see here. Beyond the disk, magnetic fields come into play. Because it's so hot, virtually all of the gases we are discussing here are ionized. The inward spiral of these ions generates a magnetic field. As you can see, the magnetic field encircles and guides the ions and electrons rushing out of the vicinity of the black hole. The rocket nozzle model explains not only double radial sources, ones coming out of each side of the accretion disk, but also the jets and beams we see protruding from other active galaxies we have discussed so far in this chapter. The major difference between the different type of active galaxies is the angle at which we view the central engine. Like you see here, where the observer looks directly into the jet, the observer sees a blazar or a BL-like object. If they're looking at it from an angle, they see a quasar. And if they're seeing it directly parallel to the disk, then they see a double, or to the plane of the disk, they see a double jet or a double radial source. And then you can also have gravitational lensing of these quasars that show you different images for the same objects, such as this Einstein cross, which is all the same quasar, just being lensed in different directions by different objects or gravitational fields or warped space-time, whatever you want to call it, that it passes through.